then I think we are good to go. So first of all, thanks everyone for joining today's talk. And please join me to welcome Mike to join us today. And yeah, just brief introduction of Mike. I'm pretty sure you all read his bio. So Mike did his PhD in UK, in Bristol, and he did his work together with Professor Dima Damen, and then he continued there as a postdoc, and now he is uh, like senior lecturer. So translated to our vocabulary, it's assistant professor also at the University of Bristol. And he has done a lot of work, in particular, very famous in the egocentric domain, like the HD EPIC, the recent dataset going back Ego4D, also the part of the Ego4D big effort, and also the very beginning the EPIC kitchen dataset. So that's had led to really a lot of follow-up work in egocentric vision and nowadays in embodied AI and so on. And if you read, Mike has also really cool thesis. Let me read the title, which is titled as Verbs and Me, an investigation into verbs as labels for action recognition in video understanding. So today, I'm really curious what Mike is going to tell us about video models. So Mike, please take it away. The floor is yours.
Okay, yeah, thanks for the introduction, and thanks also for the invitation. So yeah, I did label this a bit clickbaity, I guess, as a title. So why do video models struggle on real world data? But so I won't go into why video models struggle on everything, but there'll be a subset of things. So I'm planning to talk about three of recent projects that we've completed here at the University of Bristol, and yeah, start to uncover what's kind of left for video understanding and what things I think we should be paying attention to as we're going forward. So, well, yeah, I guess the introduction did most of it. I've started as faculty 2022, so that's 4 years ago now. Time is flying. Part of the machine learning and computer vision group, and this is kind of our latest gathering with a picture. So there's quite a lot of us now at Bristol all working on machine learning and computer vision. Okay, so the first work I was going to talk about, it's on archive now. The title of the paper, at least, is "A Video is Not Worth 1,000 Words," but really is kind of investigating are videos necessary for a lot of tasks. And I'm going to start off with, I know it's a bit late on a Friday, but hopefully you can kind of think about this problem a bit. I have two frames from a video, and as a question that we're going to ask a model, or I guess I'll ask you, is what is the primary purpose of the cup of water in this video? And the question really is asking you which frame is more important. So the left-hand frame or the right-hand frame. I'll say, I don't know if it's coming across on Zoom very well, but hopefully you can see someone has put a paintbrush in the cup of water. So just bear that in mind, what you think, which video should be more important for asking this question, and we'll come back to this later. So in terms of video understanding itself, so historically this has been a classification task. You might be given a video such as this. I'll just turn down that of someone rolling up a cereal bag and placing that in a box, and you be asking a model, can you classify this into one of several classes? So you put this through your model, has some weights, and say 14 is the class which corresponds to put away food. You'd hope that your video understanding model would classify this as class 14. With bigger, stronger, and maybe better models, especially recently, a new task has become more common, and that's of video question understanding. So you'll be given a video, you'll be given the question, and then the idea is, can you, out of a select set of options in the closed visual question answering task, can you choose the corresponding option that relates to the video? And hopefully, I'll just play the video again. When the video is being played, you can look at the answers and make the right decision that C is the correct answer here. So they're rolling up the cereal bag and putting it into the box. Okay. So this problem is like inherently challenging, right? More so than we had before, because we've now got a lot more things at play. We've got the video understanding part, we've got to understand the questions, and we've got to understand the answers. So we now need to comprehend many different elements, and we even need to now perform some cross-modal understanding. So before, when we were just predicting the classes, you're kind of just doing that within the context of a video. The model might not exactly know what the class means in language terms, because that's just what we've ascribed to the class. But now in this video question answering task, we now have to do this cross-modal understanding. So there's a lot more elements, but there's also a lot more that can go wrong, which, yeah, I guess a bit of a spoiler, we find out. So let's go through that. So like I said, this task is not necessarily new, but is now kind of become a lot more common, especially in the era of multimodal large language models. Um, and previously and historically, there's been a lot of issue regarding the bias and underrepresented modalities. One of the kind of big papers in visual question answering, at least, they found that whenever you asked a question, the answer is always yes, or if you asked how many, the answer is almost always three. So you can almost like have this model completely short circuit, ignore the question, ignore the visual input, and then just short circuit on these answers. So with this knowledge in mind, we should really kind of be careful about this because this task is quite easy to have these issues. And I guess repeat some history. Okay, so that's kind of the focus. We were looking at, is this still a problem? How do we quantify this as a problem? And particularly in this work, we do this with Shapley values from game theory. And as an intuition, I will go through the details, but the idea is each input or each part of the input is given a score of its importance with respect to the final decision. So hopefully you'll be able to know which parts of your input are important for the model to make its decision and hopefully the correct decision. Okay, so Shapley values were introduced by Lloyd Shapley in 1951, and this was in the field of cooperative game theory. So you'd be all playing a cooperative game, and you can give an award to a participant, which is basically how much credit or blame that the final result happens. So if you won the game, then you can see, who is the most valuable player, and if you lost the game, you could say maybe who do you not want to play with next time in order to win the game again. The nice thing is it has some kind of good mathematical properties. So with respect to kind of fairness of how the awards are assigned and symmetry and so on. And this has been used if in some machine learning before to try and do other tasks, so videos and also kind of images as well. So we're kind of extending this for video question answering. So how does this work in practice? So we break our input down into atomic inputs. So these are kind of like the smallest things that we can represent. So let's say we've got our input that's broken down into four items. We calculate the individual contribution of each input based on the output. So, and this uses the power set of all inputs. But as an example, so let's say we start with this kind of red item. This gives us a contribution, positive contribution compared to just inputting nothing into the model. If we now add the yellow item, we get a bit of a larger contribution. Hopefully that came across okay. And let's say we remove the red and then added in the green, we now got a negative contribution or a negative result. We can like kind of see what these differences are and kind of use this to calculate the contributions based on this entire power set. So we can keep doing this. This is kind of the formula. So you have the set and you're basically adding in an item I or not, so that you're already sort of changing one thing as another. V is your function, which is kind of getting you your reward. So this is calculating the Shapley value. So basically what we're saying is the output of the model with item I, what's the difference between that without it? So that's what this part is calculating. And then we're doing this kind of over the entire power set. So there's a lot of big scary factorials in there, which means it's quite expensive. But essentially we can kind of get for each item how beneficial or how harmful is this for the final result. There are a few things to think about. So the power set means this is very expensive. Just think, how many tokens might go into these multimodal large language models, as well as kind of what we choose to be an atomic input, because this could have a huge effect in how we do this calculation, as well as what does it mean by an empty input for these models. Okay, so in practice, we approximate the Shapley value via sampling. Even at Bristol, we have our new Isambard AI supercomputer. We still don't have the compute to do this full non-approximation. So we choose 5,000 samples, which you might think that's not cheap because we're running inference 5,000 times for an example. However, what we find is if you're trying to do this on your own model or your own data set, this works to around 40 GPU hours, which considering about the training cost of a multimodal large language model, this kind of really is a bit of a blip in comparison. So we think it's kind of worth it, even though it's not a cheap operation that you want to run all the time, but just to check what's happening. In terms of what we define the atomic input, we choose frames and words here. And this was purely to be closer to the human perspective. I mean, ideally, we want to get down to the pure token level, but I think this kind of leads to a lot of potential issues with, especially from the word side. What does it mean when we have parts of words being beneficial and other parts of words being harmful? It can be hard to reason about this from an explainability point of view. And in terms of frames, if we were to break this down into the patches, we probably had to run even more samples than 5,000. This wouldn't be anywhere near enough, so we'd probably end up costing even more GPU hours, which we didn't really want to do. For the empty input, again, there's a lot of good options here. There's an argument being made for if you just kind of remove frames entirely, but then how do you pass through nothing into your LLM and expect something? So we set the values to 0 overall. And in terms of the text, then we just have the empty string for text. Okay, so with these Shapley values that were calculated on the output of this model, we can now define two metrics. So remember, these Shapley values are just giving the attribution of how important each input is. But we want to do kind of higher order things with these. The first is we do the per modality contribution. So we look at the ratio of the total absolute contribution per modality. As an indication, this gives us how important is each modality overall. And here we've got three modalities, or we're treating them as three modalities. We have the video, we have the question, and we have the set of answers. And then we also have the per feature contribution. So really zeroing in on those features. What is the average absolute contribution of each feature within a modality? And this gives us an indication of how important is each feature on average per modality. Okay, so what does this look like? So I've got some frames from an image here, and they're colored based on if they are a negative importance or a positive importance towards the final answer. And this is the kind of correct ground truth answer here. So we're saying that certain frames, these blue frames here, are important to the model getting the answer wrong. And basically, if these frames are in red, they're kind of more distractors and actually would be helpful, or the model would be more likely to choose the correct answer if these were removed. So one thing to note is you can see that a lot of the frames are red. So that's basically saying a lot of these frames will be harmful to the model. Next, I'll show the question. So this says, summarize the primary activity that is involved throughout the video and identify the tools that are being used. And then we have the answers here. So we've got 5 answers. The ground truth is the top one. So C, which is the person in the video, making a basket out of bamboo strips. So this is kind of what these look like. And one thing immediately that you can hopefully see is basically how close to 0 the video frames are in terms of like the paleness of the colors compared to the words in the question and in the answer itself. Interestingly, there are some kind of nice cases where it's like making basket and bamboo strips are very high. So these are kind of very important for the model to choose that top ground truth answer. And there are a couple of cases where you can see the items which do match the question and the answers that it chooses. This is just one example. So in reality, we looked at 6 different models over 4 different data sets. For each of these data sets, we had to subsample, so around about 50 to 60 questions per data set, just to keep this cost down in terms of calculations. But what it showed is it consistently showed that methods are not utilizing the video modality anywhere near as much as the other 2 modalities. So this is this modality contribution. So again, this is kind of just like summing up all the contributions within a modality and then creating this ratio. So you can see for almost all of these models, apart from Video Llama 3, which I'll talk about, have quite a low video contribution. So these are quite low in terms of red. The question, surprisingly, also doesn't have that high of a contribution. And the models are really just looking at the answers. So you can kind of say they're trying to just do this matching task of matching the video to the answers, more so than maybe looking at the question. But really, a lot of their time is spent looking at the answers, or a lot of the contribution comes from the answers. Now, immediately, this kind of felt odd to us, but when we thought about it further, if you think about doing a multiple choice exam, you probably do read the question, and then you're really trying to work out which is the correct answer and trying to remove certain other answers. But we really feel that the video should have a higher contribution here. So Video Llama 3 is the more recent model that we tried, and you might think, oh, but this looks promising because the newer model has a higher modality contribution. And that's because we're looking at the contribution of the modality as a whole. And because Video Llama 3 just samples a lot more frames, I believe we had 180 frames. It might be 120, I can't remember the exact details, but basically we had a lot more frames sampled. So when you sum that up, that just corresponds to a greater modality contribution. But the per feature contribution, which we have the results in the paper, it's much more in line with the other models, and actually it's a lot worse. So the only spark of hope, I guess, we have is kind of lost in that it's just because this Video Llama 3 just samples a lot of frames. On average, the frames that Video Llama 3 uses do not contribute anywhere near as much as the question, and especially not the answer. So not the greatest of news. This is the example from the very start of this section of the talk that I showed you. So you can see the two frames here. And interestingly, the frame with the glass of water, with the person dipping the paintbrush in, has a negative contribution. So removing that from the video would actually help the model to get the correct answer of cleaning the paintbrush. So a very, yeah, a not very good result for the model or for video question understanding as a whole. Okay, so a bit of bad news so far. Is there any hope? Wow. One thing that we looked at when we were when we were creating HD Epic and we were looking through a lot of the VQA benchmarks is almost all of them use 5 answers, which makes sense. This is kind of what we're used to at school. There's some statistics to show that if we have 5 answers, even random guessing, it's very unlikely to get a high mark. But we kind of wanted to test what happens if we keep scaling this further. So if we added in more answers, what would happen? And so what we did is kind of very naive. We basically took answers that we from the other questions within the same data set, did a very easy, quick check with like semantic similarity via a model to make sure that they weren't too similar. But we just randomly shuffled in answers from other questions and added them into each question. So what is this graph showing? So the default, that's the original setting where we have 5 answers. Easy is what happens when we have the correct ground truth answer and 4 answers from other questions. So it almost doesn't make sense, right? So you'd be asking the question, what is the use of the glass of water? And then you might have something completely arbitrary, like to hammer in the nails, right? So these shouldn't be hard answers at all. And then where the next 4 settings is where we're adding in new answers. So we're adding in 5 new answers, which again should not be hard. They're kind of easy negatives, adding in 10, 15, and 20. And we were kind of surprised to see. So, sorry, I had the legend on this slide, but what we were surprised to see is that, let me just go actually to the full, is that consistently in the video modality, so this top left is the video modality, is as we add in more and more answers, even silly answers that wouldn't even feel human, our contribution of our video modality is getting higher. So by making the problem harder and putting in more answers, our models are naturally going to look at the video modality a bit more. So that's kind of promising. Interestingly, they also tend to look at the question a bit more as we add in more and more answers. And because it's a ratio, then of course that means that the answer modality is getting less and less important as a result. In terms of accuracy, you can see that the models do get kind of steadily worse. In some cases, quite a bit worse, but mostly especially in the more powerful models, they tend to kind of plateau. Again, because these are not hard answers, they're kind of completely irrelevant. But this does mean that even with some kind of trivial answers, we're actually seeing some nice effects towards improving models using the video contribution, using the video a bit more to answer the question. So one thing I would say is that if you are planning on making a video question answering dataset, maybe suggest having more than 5 answers for the models to choose from. Now, a lot of people, when we talk about this project, have asked about open VQA. So closed VQA is when you have the answer set given to you. In terms of open VQA, you want a model to generate the answer. Now, there's been a whole host of issues with evaluation. The current state of the art is using LLM as a judge in order to judge whether the answer that the model gave you is correct. In this case, we just use RougeL, which is a captioning metric, but essentially takes 2 captions. So the caption or the answer that's generated from the MLLM and then compares if this is close enough to the ground truth and gives a score between 0 and 1 based on this. And with this score, we can actually directly use this to calculate the Shapley values because we just need to know whether an answer gets better or not with or without some input. And this is kind of a subset of the results, but you can see, and initially it looks good. Video Llama 3 uses the video modality 69% of the time, or a 0.69 ratio. However, this was kind of the same thing that I talked about before, and when we go towards the per feature contribution, so how much is the average feature within that modality contributing to the answer, you can see that the question and the text is really dominating across the different data sets. And the only reason why these modality contribution scores are high at all is, again, like I said, because Video Llama 3 uses a large number of frames. And even if you have a small amount of contribution per frame, the more frames you have, the higher the contribution is going to be. But as a whole, on average, those frames do not contribute very much at all. So this is still a problem with OpenVQA, and yeah, something that needs to be looked into. The one thing we can say is because there is no answer modality, the models are no longer focusing on that. However, they do seem to be short-circuiting through the question and the text modality. Okay, so what's the overall outlook? Models are consistently underutilizing the video modality when making up their decision, especially in the video question answering task. The positive seems to come solely from just the token length, which is not necessarily a good thing, because it means that even though there's more video frames going in or video tokens going in, on average, it's not using them anywhere near as much as the textual question or the answer. I didn't show these results here, but we actually found that datasets can be answered blind or with no questions. So removing the video modality didn't make too much of a change when we ran the results. And that kind of shows that stronger negative answers are needed. But also, there is some hope in that increasing the number of answers in the closed VQA setting can start to help with this. And this is something that can be implemented with very little effort. Okay, so if you're interested, we have the paper on archive, and you can follow the link there or the QR code, and there'll be the code as well as the dataset subsets that we used. Okay. So that's the end of the first section, and I'll start talking about the next one. So this title of Stop Models Gaslighting Us, I think this is a work in progress title that I came up with, but both Kevin and Dima said we can't call the paper that, which was a bit sad. So instead we came up with a much better title of Moment of Untruth, Dealing with Negative Queries in Video Moment Retrieval. So this was published at WorkV last year. So I'm going to get you to watch a video, and then I'm going to ask you when a moment in that video happens. So you just got to think if it's towards the start of the video, towards the middle of the video, or towards the end of the video. So I'll just play the video itself. So this is from Ego4D and recorded during COVID, which is why in a minute the person pulls off their mask. Okay, so that's the short clip. And the question is, when did aliens attack from the sky? And hopefully, if you're paying attention, you would realize this never happened in the video. Yet when you would ask a model, the model would come back and say, this happened between 1 second and 10 seconds in the video. And this was because in the video moment retrieval task, so this is the task where you give a model a query and a video, it's meant to find the moment of when that query happens in the video. And the assumption, which I'm labeling as dangerous here, is that the video moment retrieval model always assumes that the query exists in the video itself. So the methods are always been trained such that this moment occurs. So when you ask it these insane questions or insane queries, which didn't happen at all, they will always give you an answer and always strongly recommend this answer. And basically the models will hallucinate these answers even when no such action exists. So what we wanted to do is actually try and make these models negative aware, and basically by adding in negatives, hope that the models can now distinguish between positives and negatives and actually tell you, no, there weren't any aliens that attacked from the sky. But we do need to be careful here in what we define as a negative. The main thing is if we used an LLM to rephrase queries, how do we know this doesn't happen in the video? So a lot of these video datasets, or at least the datasets used for video moment retrieval, they haven't been labeled densely. So there's potentially actions in this video which we don't know whether or not were like, so they weren't labeled, but we don't know what's in the rest of the video. And we don't have to check every query in every video because this is quite expensive. So what we want to do is make sure that ensure that the new query makes sense and is in the same domain to actually make it a challenging negative. So we might have a query here in the video, pick up the onion from the countertop, and we want to kind of subtly, change this so it's still within the same domain, but we might have a caption which says place the onion in the fridge. So this, might not happen in the same, well, hopefully doesn't happen in the same video, but this would be an example of a negative that we want to find. So what we do in practice is we shuffle queries across different videos, and we ensure that the kind of semantic similarity between these shuffled questions are kind of low enough that they don't occur in the video. So this leads us to two things, which is useful. One, the queries are in domain, so they're within the same context of the data set. And two, we make sure that we don't have this problem where we have false negatives. But this is for in domain, and we also want to check out of domain because maybe models are good at one of these or not the other. And we want to kind of test the full kind of range of negatives. And in practice, we do actually generate these with an LLM, as long as we choose the correct domain, which doesn't overlap with the datasets themselves. So in our work, we use two datasets, so QV highlights, which is news and vlogs, as well as Charades STA, which is a lot of home scripted videos. So in practice, we choose a lot of different domains to generate the queries. So we have competitive sport, animal behavior, a physics lab, as well as mathematics classes. So we're asking questions in these domains generated from an LLM and making sure that they don't match with the video. So this is an example. So we have this video here. It's 150 seconds long. A positive query might be a man in a flannel shirt crouches to point out a hole in the ground. And we have a bunch of negative queries. So these are from the same data set, but on different videos, because this task is done on a video by video basis. So you can see they're kind of similar enough. So men in formal attire standing all together on a beach, but not actually relevant to this video. And we have a bunch of out-of-domain negative queries, which are completely different to what we might be expecting. Such as like an octopus carries a coconut shell using it as a portable shelter. We know that doesn't happen anywhere at all in the video. Okay, so with these negatives, the first thing we want to do is check how severe this problem is. So we've got a model here, UniVTG, and we're testing this on QV highlights first. And this indicator score is what the model uses to determine where the moment it should predict is. So this is a score between 0 and 1 basically saying this matches the query very strongly, and 0 saying this doesn't match the query at all. And hopefully it comes across okay, but we have positive in blue, the in-domain negatives in orange, and then the out-of-domain negatives in green. And what we can see is that there's basically no difference between what the model thinks is a positive, in-domain negative, and an out-of-domain negative. And we thought, okay, this is surprising, how much they overlap. Maybe it's just UniVTG. So we tried a different model, CGData, and got pretty much the same thing. So again, this is the indicator score, which these models are using for this video moment retrieval task. And these models just cannot tell almost any difference between positives, negatives, either whether they be in domain or out of domain. And in a lot of cases, these are, very, very different. So we were really worried because it's like, maybe we missed something. Surely someone has looked into this. And there was a little bit of ray of hope. Now, saliency score is not used in the video moment retrieval task. It's actually used for highlight detection, and that's where you're trying to find multiple moments which might match with a query. So the saliency score, which has again been trained, these models can do both tasks. So even though this is not used in video moment retrieval, they gave us a little ray of hope that not everything was lost. So you can see there's some separation between positives and the in-domain negatives and the out-domain negatives. A little bit overlap, but not too bad, all things considered. And we thought, okay, maybe this isn't as much of a problem as we thought. So we tried on another data set. And we tried on Charades STA. Again, the indicator score gave us a very similar effect. But we thought, okay, let's look at the saliency score again. Hopefully this should be fine. And it's a lot more muddled and a lot more overlapping. And Charade's STA wasn't actually labeled with ground truth saliency scores. So a lot of these models are kind of emulating this or synthesizing this when they're being trained. And it seems that if we don't have the ground truth saliency score, then these models really can't tell the difference between what's a positive and what's a in domain or out of domain negative. So that was surprising, but we then thought kind of, how do we fix this? So we're going to start super simple. We have our video as our input broken up into frames. We have our query. So in this case, man in pink top eats fish. We're going to pass this into our video moment retrieval model. And this is kind of a general task, a general method that you put on top of many different models. So put this as a kind of a generic thing here. So we get three outputs. We get the indicator, which is this red box. We get the saliency score. So this is the orange box. So normally this isn't used at all in moment retrieval. We also get some offsets, but that's just for calculating the start and end times, but aren't as important here. We pass these through a good old RNN and then a fully connected layer or feed-forward network, and then we get our classification. And this is a binary classification as to whether the model believes that this is a positive or a negative. So, it goes through, it sees the video, it sees the query, and then we just check based on the indicator scores and the saliency scores whether or not we can see whether something is a positive or a negative. So what happens when we test the original models? So this is UniVTG. So these are recall at 1 an MIU of 0.5. So just basically checking, can you get the predicted moment in the top one with a certain IOU threshold? And then on the right, we also have our two new metrics, which is the in-domain accuracy and the outer-domain accuracy. And we can see for UniVTG so this is the previous model, state of the art at the time, it's getting about 10% right, which is pretty bad. When we tried other models, so CG and QD we see the same things. Hilariously, they're even worse on the in-domain and out-domain accuracy, so they really can't tell the difference between positives and negatives. And then we kind of started training our negative-aware models. And what we can see is this is not a hard task, especially on the outer domain accuracy, where we're getting close to 100% performance. The thing to say is that we do see a little bit of drop in terms of the recall at 1, but we think across the board, this is much more useful to have a model which can actually tell you whether or not your query occurred in the video or not. So this is on QV highlights, and then we have the same results on Charade's STA. So interestingly, it's harder to do the in-domain negatives in Charade's STA compared to QV highlights, but still the outer domain accuracy is very close to 100%. Again, these are kind of completely different, so this should be quite easy for the models to determine. And when we look at what's happening with the scores, so you can see now the indicator scores have been completely separated. The saliency scores a little bit in some cases. You can see here that the in-domain negative has still got quite a large overlap with Charade's STA, but really it's the indicator scores which have shifted so much so that the model can now actually tell which is positive and which is negative. Okay, so just to conclude this section, so video moment retrieval models kind of suffer from not being trained on negatives. So they've always been assuming that the query that you get must occur in this video. We can keep most of the performance, even with this very simple way of training with a binary classifier output. But there's a little bit of trade-off between positive and negative performance, but we think this is important going forward. And saliency scores, which historically have not been used in video moment retrieval, can go a long way of solving this issue. Okay, so this is the paper. Again, it's on arXiv, and you can find the link to the code and the models that we used here. Okay, so I'm going to move on to the last section now, which should hopefully take us up to the last bit of the talk and still leave some time for questions at the end. And going to give them this title, Searching the Unknown. So the paper title, Beyond Caption-Based Queries for Video Moment Retrieval. So still on the same task of video moment retrieval. And this was in collaboration with David, Albert, Dima, and Sergio, and will be presented this year at CVPR. Okay, so when we were kind of looking again at video moment retrieval, what we found is a lot of the captions for the video datasets contain a lot of information. So I'm going to play this video of a moment here. Just turn off the sound. So this is someone at their kitchen. They're making a recipe. I think it's an egg sandwich or something, and they're just cracking some eggs into a jug. But the example caption for this moment is quite detailed. So we get add the last two eggs into the measuring jug, tapping them against the countertop to break the shells before cracking them open. And if you were kind of searching for a video through this video for a moment, so you might want to know, say, how many eggs to use in the recipe. You're not going to give a caption, or you're not going to ask the model something similar to this caption here, right? You're not going to write out this whole long thing. I mean, similarly, when you search YouTube or Google for certain parts of a video, you're not going to type out this very, very detailed thing if you're don't know what the video is that you're trying to find, or you don't know what's in the video. So we see this disconnect between the way that these data sets have been labeled and the way that people kind of use them when they're doing this task. And specifically that this kind of search is a lot less specific. You don't know when they're kind of are cracking the eggs, what order they're cracking the eggs. You just kind of want to know how many eggs to use in the recipe. And this is because of the annotation process leading to this kind of bias. And the way this is or the reason of this is because when we are annotating these data sets, they're originally being annotated for captioning. So you watch the video, the video gets passed into our annotator, and then they come up with a caption, and they come up with the start and end time of that video of what that caption applies to. But that means that they've kind of watched the video, and this caption has been made knowing exactly when this happens in the video and exactly what happens in the video. However, when we're searching, you might be asking questions such as when are the goals being scored? Because you don't know when they happen in the video. They might not happen at all in the video, or there might be multiple cases, right? So you haven't seen the video necessarily. And so the models should be able to kind of deal with this, but we can see this big disconnect in the types of queries that people are using. And we kind of label these caption-based queries. So these are the standard queries that people have been using in this task. And we can kind of compare these with search-based queries. So these are the queries that we're saying in practice when people are searching through videos or video corpora, they're more likely to use a caption like this. Again, the first thing to ask is this actually a problem? VLMs train on so many captions. Maybe the search queries are not out of the domain. Maybe they can do this anyway, and this isn't actually an issue. The first problem, though, is we need a search query dataset. So let's look at this problem. So search query datasets don't actually exist. Like I said, when people are annotating the video understanding data or the datasets for video understanding, especially captioning and especially for video moment retrieval, they're all repurposed captioning datasets, which means that the annotator has watched the video in full and they provide a lot of detail as they're going through to make this kind of unique. And this is good, right, for your model that you want to do fine-grained understanding and fine-grained captioning. But in practice, when we're trying to do this kind of matching and query search, this is not what we want. So instead, we have to synthesize search query datasets from existing datasets. It's quite hard to annotate these search queries naturally because, again, we have to kind of give videos. We'd have to ask people to come up with a query which they think might happen in a video. And no one's done that, and it will just take a lot of time. So instead, we kind of synthesize this, and we can use an LLM to create less specific versions of original captions which match this search query idea. So if we have our original caption here, a girl baking a carrot cake with her mother, we pass this into our first LLM to underspecify it. So this gets down to a person baking. And then we pass this through another LLM to kind of validate just to make sure that these two match. If they don't match, then we ask a human annotator to go through and kind of rewrite this to make sure that this does match and that we have a nice clean set of annotations. But we now have a new issue, is that when we go from specific moments or specific queries, which might align to a single part of a video, we now might have multiple captions that align. So this kind of could muddle the matching and causing us a bunch of issues. So we might have two captions, a person baking and people prepare a cake, and these could very well explain the same moments. So what we do is we have to have this grouping stage. So these are the two moments that I talked about, or the two queries that I talked about. We group these together, again, based on semantic similarity, and then pass these through a final LLM agent, which then converts these into a general query, which matches all of these moments in the video. So we've gone from this original caption into this search query, with multiple moments that it relates to in the video. So this is done on a per video basis. Video moment retrieval still focuses on searching within one video. There is a corpus task which goes beyond one video, but for this paper, we're just focusing on the moment retrieval task. And this basically gives us a set of new datasets which contain search queries. So we started off with HD Epic. We had 156 videos, almost 60,000 queries. Every query matched to exactly one moment. So we had no queries which had multiple moments, so 0%. And when we did this first round of under specification going towards search queries, you can see our number of queries or unique queries dropped. So a lot of queries kind of got grouped together. We had almost 9,000 multiple queries and almost 25% overall. And we could do this a lot of times. So one of the things we did in HD Epic was just add an extreme amount of detail to all of our queries or all of our captionings. So we can actually do this 3 times and ending up with what we call HD Epic S3. So this is the most underspecified, most like kind of query, search queries that you might find. You can see we've kind of cut the queries dramatically down to only 10,000 unique queries. Of which 5,000 of these are multis, this turns out to be about 50% of a data set will align to 2 or more moments in the video. So we're really expanding from a one-to-one mapping, which is very common in these data sets and in these methods, onto a kind of 2 or more to 1. Okay, so back to whether or not this is a problem. We have our search query dataset. The next thing is we now need an evaluation protocol because we're going from this one-to-one mapping to now a multiple to one, a many to one. These search queries are more general and now non-unique, which leaves us a problem with recall at 1. As each query might map to 2 or more moments in the video, we need to now not penalize if a highly relevant moment, which is matching the query, gets ranked above another. And currently, recall at 1 doesn't take this into account. So we update the evaluation protocol. So like I said, recall at 1 enforces that the ground truth moment is first, even if relevant moments are ranked above this. And in this leads to cases where plausible moments are ranked higher than the ground truth moment, because originally these datasets were annotated one-to-one. So we want to make sure that these other plausible moments that were found during this search query stage aren't kind of penalize the model for putting these high up in the ranking. So what we do is we allow for other kind of these ground truth moments, which we've found via our method, to also be treated as correct if they're ranked higher, with the caveat that no incorrect moments can be ranked higher. So what does this mean in practice? Because this is quite confusing. We label this multi-moment recall. So what this means is if we have a ranking here, we have our video and 2 moments which belong to the query. And this is our ranking. So we have one of the moments ranked high and one of the moments ranked third. In recall at 1, this will be given a 1 because this moment is ranked high. And in our multi-moment setting, this would be given a score of 0.5 because although this moment was ranked highly, this moment was not ranked above incorrect ground truth moment. So you can see here, this would be 0.5 because this one was correct in terms of rank 1, and this is rank 3, but an incorrect moment was ranked above it. In another setting, if we have both of these moments ranked, first and second, then we give a score of 1, so exactly the same as recall at 1. And in the case here, nothing is correct because there's always an incorrect moment that was ranked higher than one of the ground truth moments. So at its core, when we have 1 moment per video, this multi-moment recall does kind of go down into recall at 1. So they are kind of equivalent at that case. But as we're expanding to multiple moments, which you can see from the results that I showed before, where almost 50% of HD Epic S3 had multiple moments, we kind of really needed to update this evaluation protocol. And we did a similar thing for mean average precision as well. So you can find those the details in the paper, but essentially doing the same thing where we're now keeping track of all the ground truth moments or potential ground truth moments in the ranking, not just the specific one that was originally labeled as part of the dataset. Okay, so with all that, we can now answer the question of, is this a problem? And what this is showing is we have a couple of different models here, so CG Data and LD Data. We can show what's happening to our recall as we're going from the original dataset to the S1, S2, and S3. So these are getting less and less specific. So we're going from a more specific here to a less specific here. And we've also got this on UCook2 and ActivityNet captions. And you can see basically that the recall scores are dropping hugely as we are increasing, sorry, or as we're decreasing the specificity of these queries and going towards these search queries. So we find that as the queries are getting less specific, our performance is dropping. And so we can't just hope that these models have been seen enough captions to learn around this. The next thing you might ask is why? So we looked into this too, and we split these results up into whether the query is a single query, so it only ever has a one-to-one mapping, even under the under specific or search query setting. And we then split it into multiple the queries which are multiple under the under specific. And what we see here is that basically there's a drop regardless. But there's two kind of gaps. One is a language gap and one is a multi-moment gap. And you can see that part of this gap comes from going from one query matching one moment to multiple moments matching a query. These models haven't been trained to deal with this. So remember from the assumption in the last part, these methods assume one moment and one moment only. So we fixed the zero case, and now we're fixing the multiple case. And the other reason is because of this language gap. So even when there's a single query that's underspecified, we still see this consistent gap. So yeah, we kind of know there's two reasons behind this, why these models don't scale well from the caption queries that they've been trained on to the search queries that they've been tested on in practice. Okay, so you might think, how do we solve this? One thing would be to simply train on the search queries. But what that means is we would then end up with having to create these search query datasets. As I said before, these are not easy to create. You almost need to prime your annotator to kind of write queries that might happen in a video that they don't know that much about. So they have to kind of write these low detail but still somehow relevant queries, which could be quite hard to annotate and check. So the other problem is we now have to retrain all of our models, right? So every model that we have now, we have to retrain it. And ideally, we wouldn't want to do that, or at least not have to do that fully. And one of the big problems as to why they're breaking in this kind of multiple moments is because they can just never predict more than one or two moments. So ignore the purple for now. But if you look at CG Data, even with 14 ground truth moments in the video, it's only ever predicting 4 active queries. So it's a data style model, so it has these kind of queries which it uses to try and find the moments in the video, but it's only 4 of them are ever active in the kind of resulting inference step, even with 14 moments. So it really just doesn't scale at all. So that was kind of one of the things that we needed to solve. And the reason why we have this kind of decoder query collapse is twofold. The first is a coordination of collapse. So self-attention within this decoder. So we're passing in these queries into our model. They're doing self-attention and then decoding to try and create these, to find these moments. But what that happens is the self-attention allows these queries to kind of coordinate together and basically says if one query believes it's got a good match to our text query, a lot of queries here, then it will kind of suppress and push down all the other queries within the model and basically lead to this collapse. The other one is an index collapse in that because of this single moment prior, the model itself is kind of only allowing certain indices or certain like specific queries to dominate the output confidence. So we see kind of a subset of these queries. So the common number is we put 20 queries into our data style model, even though we're only ever trying to find one example. And only a small subset of these are really ever allowed to predict the moment because there's no need for all of them. And so we find there's actually 2 relatively simple fixes. The first is just to remove self-attention within the decoder and add in query dropout. So we have a small chance that we will drop out each query in the data style models. And by removing the self-attention, we can actually fix these. So what does that look like in practice? So we go from a score of 25 up to 30% for HD Epic S1, and then across the board we're kind of increasing in performance for both the single case and the multi-case. So this is helping in both cases, not just when there's multiple moments. And we see a kind of similar story on UCook 2 and also ActivityNet captions. So what this means is that we can kind of train our models still on these on our caption queries. So these are the general queries that have been labeled as part of the dataset collection. And then we can test these on our search query datasets or apply these to kind of more real world settings and improve that. And if I go quickly back to this, you can see even though we're not having this nice linear scaling, there's at least a little bit more scaling as we're increasing the number of ground truth moments when we do this removal of the self-attention and the query dropout. We do see it scales a little bit more, but it's not anywhere near perfect, but this simple trick can help. Okay, so to kind of sum up, users won't necessarily know what's in a video, which is why we're kind of going beyond these caption queries to the search queries. We find that current models and datasets can be used for this, but we do need a different training recipe in order to complete this task. Otherwise, there's a big gap in the kind of language and in this multi-moment gap. But there's still lots more to do in this space. Like I said, going for multiple videos, we didn't lean too much into the language gap side of things, but this could be completed more and more in the future. And again, here's the paper. You can find the code and the models online. Yeah, I think that leaves us around 10 minutes for questions. So thanks for listening. Thanks all to the kind of co-authors for these works. You can find out more on my website, and there's a QR. So all of the works that I talked about will be listed on the website and more. So yeah, thanks for listening.
Cool. Thanks a lot, Mike, for the great talk. Yeah. Awesome. If anybody has questions, please just unmute yourself or raise your hand. It works in both ways. And for people who are in the classroom, please let us know. I don't know what's the best way, but yeah, if you unmute yourself, I'm pretty sure we're going to find a solution for answering the questions. So I can start with one. Maybe start from the first project about this game theory setting Shapley values, right? That's what it's called.
Yes. Yeah.
Yeah. I was just wondering because for videos, it's kind of like a continuous activity, right? There might be some dependencies between video frames. So if I understand correctly, the series kind of like assume that each video frame has a independent useful or not useful value, right?
Yeah.
So would there be moments where like the presence of two videos actually show something that is meaningful for the question, while each of them doesn't play any or doesn't play big role?
Yeah, so that's a really good question actually. So it's not something we've looked into yet, but that's definitely something that could happen. This is kind of assuming some independence. There are actually other approaches which go into, so if we consider this as like first order, right, where we're just going between, we're just finding frames by themselves, whether or not they're helpful. You can think of like second order where you're saying now groups of frames, are they important? Do they help, right? So you could actually calculate that. So yeah, that's definitely something you could do in the future. We're kind of assuming in this case that it's kind of so it does get taken into account a little bit in the contribution because we are testing a lot of the power set. When I say a lot of the power, we are testing these 5,000 different iterations. So we will kind of see some effects of that. But yeah, it's not kind of modeled exactly because I guess yeah, if you have which are really helpful together. That will kind of increase the overall contribution of one of those frames, but you won't get that kind of quite modeled, or you won't be able to disentangle that exactly. But yeah, no, that's something that you could kind of expand onto and going into the second order, or even the kind of like third order statistics. Although, yeah, I don't know how many GPU hours you need for that. But you could do it, and it might show some interesting things of like groups of frames could be more useful. The other thing you could do is actually kind of group the frames together. So instead of your atomic input being a single frame, it could be multiple frames. The problem is you might lose some granularity. So if you think these groups of frames are important, it might be that only a small part of one of these frames is actually contributing highly. So yeah, there's trade-offs there, but you could definitely look into that.
Yeah, cool. Thank you. Anyone else?
I guess I have a question.
Go ahead.
So when you do the Shapley values, you said, are you using just frame by frame, then taking a frame out and see what's happening, or how do you get the score that you finally get for the video?
Yeah, so yeah, another good question. I kind of like didn't quite give the whole details just for the talk, but in practice, what we're doing this video question answering. So um, we pass the video, the question, and the answers into the MLLM, and they're predicting, one of like A, B, C, D, or E, as this is kind of what refers to the question to the answers. So what we do is we take the score of the logic um, of that token, so A, B, C, D, or E. And we try and force these models to give only a single character output as much as we can. And basically, that's logic score is what we use to calculate the Shapley value. So that's the kind of change in that. Hopefully
And
that
then when
makes sense.
you like tweak the inputs, how do you tweak them? Do you just drop one frame or do you replace the frame with something?
So it depends. So ideally, right, if we didn't have to do this sampling, we would do the power set of everything, right? So you start off with nothing, add in the first frame, and then add in the second frame all the way up, and then remove the first frame, add in only the second frame, add in the third frame, all the way. In practice, we kind of just randomly sample this. So we're just like randomly adding and subtracting frames and words from the input every step. We do this 5,000 times. I believe we're making sure that they're like 5,000 unique ones and doing it that way.
5,000 frames out of,
So
so
these
this
are
is like a full video.
5,000 combinations.
Ah, I see, I see.
So because we have the video frames, the questions, the words in the question, and then the words in the answers. So if you think of if your out the length of all three modalities is like n, then you have 2 to the n different uh, combinations, right? Which is why it scales. So 5,000 doesn't actually leave you to very like long inputs, I guess. So we're still like sampling much, much less than the actual true power set size, but we've got some results in the paper which show that as it's kind of scaling, the error just seems to be getting smaller and smaller, and 5,000 seems to be a good trade-off between what seems close to the true result.
Do you think it's a problem that, for example, videos, like other frames in the videos will have information that's already needed for the answer, which the dropped frames would also vary. So if you just keep already like the frames that are not dropped, they can already maybe give the answer that's needed. So the change in the output will not be much because it already can tell it from the other frames. How do you deal with this? Is this a problem or not?
So you're starting off with 0 frames, right? So you do have a run which has no video input, and then you're like slowly building this up. So then you can work out, what's the baseline. We also have some more results in the paper of what happens if you start masking out like either helpful frames or detrimental frames. And you can actually start playing around with the model. I mean, obviously this is kind of cheating because you're using Oracle knowledge, but you can actually start like playing around and you can actually cause the models to get really high performance, even on the harder data sets like HD Epic, just by removing the certain frames which are distractors, removing the certain words which are not helpful, and then making sure that the certain frames and words which do benefit the model, and you can actually get pretty high scores. I mean, again, this is cheating because you already know how to do this, but yeah, so you can use this masking to do that.
Thanks a lot. I have another question if you have time.
Yeah, I think so.
So have you considered, or do you know if anybody already did it, of trying to use these kind of outputs or metrics you would get from Shapley values in order to enforce the model to learn better things? For example, can you compute or estimate some Shapley values of some kind, I don't know, and then use it as a regularizer during training? If you know, for example, that for 10 frames something happened, maybe you can try to force the model to really attend to specific regions. Is this possible to do or not really?
I think in practice it's probably not possible because well, as if you have like a small number of frames, it would be possible just because the power set doesn't grow too large at that point. But really, I think the reason why people don't do this as training and use it just as an inference tool is because of this computational costs, and you don't want to have to be running 5,000 iterations of inference every training loop or something like that. That's, quite expensive.
So if, for example, run it 10 times, you think it will not be so helpful? Like if you do 10 inferences, 10 combinations.
I mean, unless you had a very, very small number of frames, like 2 or 3, right? Which would be the complete. So if you had 3, then you'd only need 8. But I think most people have a lot more than 3 frames that they want to sample.
But for example, if the interesting frames are only in a subset of them, do you still need to run many combinations, or like if only 5, like 10 frames have the something happening that's giving the answer, would it be helpful to just like try to somehow figure out if these 10 frames contributed to the answer or not?
Again, it might be. It's just, well, it depends on like the total number of frames available, because that's also what you're checking, right? Because you have the number of like frames that these models are using, which starts out around about 8 or 16 up to 120. But also the number of frames in a video, and videos that are shot at 30 FPS, we're getting onto hour-long videos. That's already, thousands of frames. So that
Mm.
becomes really, really hard. Like, so yeah, even if you're only choosing 3 or 5 frames, you got to think your total bucket is actually all the potential frames, and you got to work out which of those frames are the good 3 or 5. So I think in practice, again, I don't know. You could maybe try it, but I would have thought it'd probably be too expensive in practice.
Okay, thanks a lot.
Yeah, thanks.
That's all I had. Thanks.
Cool, thanks, Fano. Anyone else have questions? I can maybe ask also like a bigger picture question, because the title, right? If we come back to that, so we see that the video models really struggle quite a bit, right? Like not looking at the content, or like not being able to really attend like the retrieval multiple moments, but rather just like, yeah, just get the answer, or even don't understand the negative questions that don't even appear. So what do you think would be the right way to deal with it? Seems like they're just like fire on multiple fronts, but do you
Yeah,
think like we need to fix them one by one, or just there's something fundamentally wrong? Or what would be the good
yeah.
next step to deal with them? Yeah.
I think yeah, it's a good question. Yeah, probably brought on by the title. I think probably a lot of these issues are coming from the data sets that we're using. A lot of the data sets, especially in retrieval, are from like 2016, which is 10 years ago now. And so they have, like, at the time they were very, very useful for kind of starting off these tasks. But really, I think we need to kind of, as a community, look into, the data that we're using should be up to date. It should be um, representing what's kind of happening at the moment in terms of models. A lot of these data sets kind of have temporal biases, or they have other biases in them. They might be even just lots of old YouTube videos, and I think kind of new data sets which aren't just reannotating old data sets. I see a lot of benchmark papers where people are taking older data sets and reannotating them, but that still propagates a lot of the issues. And also making sure that these tasks have been designed kind of with harder things in mind, right? So the fact that video moment retrieval was kind of always assuming that single caption or single matching moment, I think it's kind of really limited that real use, like real world applicability for quite a while. When in practice, there might be multiple moments or even no moments that are relevant. So I think it's kind of going back into the data sets. There's the saying, garbage in, garbage out. Maybe I shouldn't say that really, but if we have kind of good data to train our models in, then hopefully they should do a lot better on the kind of downstream tasks.
So you think like really next step would be data set and task definition, like what kind of annotations we provide?
Yeah, no, I think they would fix a lot of the issues that we're seeing in this kind of like line of research for sure.
Mhm.
I think
Mhm.
there's a lot of other issues about how multimodal LLMs treat image input, but I think that would require a lot more work because you have the LLM backbone, so the text is almost always going to dominate inside there. But I think that's a harder problem to solve.
Mhm. Yeah, cool. Yeah, we're a little bit over time, but if anybody have a burning question, please feel free. If not, then please join me. Thank Mike again for the great talk, and we learned a lot about video models. So yeah, thanks a lot for joining us, Mike.
Yeah, thanks again for the invitation.
Cool. Then thanks everyone also for joining, and have a nice weekend to everyone.